Hey guys, welcome to another video in the video lecture series on digital signal processing. Today we are going to look into ZTransforms. So let's get started. Basically, ZTransform converts a discrete time signal into a complex frequency domain representation. It's equivalent to Laplace in discrete domain. The formula for ZTransform of a given discrete signal x of n is this. It is sigma n equal to minus infinite to infinite x of n into z power minus n. So we have expanded the same thing here, and when we write the z transform for the impulse response of a system h of n, the corresponding equation we get is called as the transfer function. We know that for an LTI system whose input is x of n and impulse response is h of n, the output is a convolution between the two signals. That is, y of n is equal to h of n convolved with x of n. And from the convolution multiplication duality, the spectrum of y of n, y of z would be multiplication of spectrums of h of z and x of z. The z transform becomes equivalent to that of dtft when z is equal to e power j omega. Here are a few examples of how to find the z transform of a given signal. These here, the examples which we have taken, are time limited. We have just used the above formula and simplified them. ROC, or region of convergence, of a z transform is defined to be a subset of values of z for which the series converges. The series in the sense the summation of x of n into z power minus n becomes a finite number and does not become infinity. It's very important to know ROC of a given z transform, as it helps us to uniquely determine the inverse of a z transform. Also, we can characterize the causality and stability properties of a system. Let's see these as we go on. Consider the expression 1 plus x square and so on. It is nothing but summation of x power n from n equal to 0 to infinite. We know that from geometric series, this summation would tend to be equal to 1 by 1 minus x when mod x is less than 1. And when mod x is greater than 1, this expression would not converge, that is, its value would tend to infinite. Given a signal x of n, let's see how can we find its ROC. Consider a signal x of n which is equal to 0.5 power n u of n. We can find the transform using the formula which we had discussed previously, and combining it with the result which we have obtained here, we get the z transform of x of n to be equal to z by z minus 0.5. And as we are using the result which we have obtained here, we have to apply the same conditions also, which would mean mod x is less than 1, and here mod x is 0.5 z inverse, which would mean mod z is greater than 0.5. This can also be geometrically represented here, where we consider a z plane, and then the ROC would be the region excluding mod z greater than 0.5. We know that mod z equal to a represents a circle of radius a, and here a is 0.5. So the ROC would be the entire z plane from which a circle of radius 0.5 centered at 0 has been cut out. Another important thing to note is that two signals can have the same z transform, but they would have two different ROCs. Consider another signal x of n which is equal to minus 0.5 power n u of minus n minus 1. Its z transform, which can be found using the formula which we have discussed previously, would be this. But the ROC would be mod z is less than 0.5, which can also be found out from the previous results we have obtained. Here, if we observe, the z transform of this signal and this signal are the same, but their ROCs are different. Thus, an ROC helps us uniquely determine the original signal x of n even when we have Z transforms of two or more signals being equal. We can actually generalize from the previous two results the following expressions for Z transforms. And these represent the ROCs for equation 1 and equation 2 respectively. So this would be a causal case and this would be an anti-causal case. Causal is because we have only inputs from n which is greater than 0, but here we have inputs which are of negative time and thus it is anti-causal. Now let's see some common Z transforms. It's ideal to actually be able to derive Z transforms of any signal, but knowing the Z transform results of a few basic signals would make it easy to solve when we are dealing with complex functions. So you can actually try to represent the complex function as a combination of easier functions and thus find the Z transform easily. So these four here can be found out directly from the previous results with a equal to 1 here and a equal to minus 1 here. Now let's see how can we find the Z transform of a cos. So this is the cosine function we have, which is cos of omega naught n. We can represent the cos in its Euler form and find the Z transform of this component and this component separately and then combine them back to get the Z transform of the required signal, which is cos omega naught n into u of n. So h of z here is 6 minus 10z inverse plus 2z power minus 2 by 1 minus 3z inverse plus 2z power minus 2. We have seen in the previous slide that h of z is equal to y of z by x of z. So given a h of z, we can actually find the input-output relationship of a system, and let's see how. So what we do is we cross multiply these two terms. So we get y of z into 1 minus 3z inverse plus 2z power minus 2 is equal to x of z into 6 minus 10z inverse plus 2z power minus 2. Now applying the inverse Z transform and using the time shifting property, which says that if x of z is the Z transform of x of n, then the Z transform of x of n minus n naught would be z power minus n naught. So here z power minus 1 would indicate that it had been shifted by minus 1 and minus 2 would indicate that the signal has been shifted by minus 2. Using the above stated properties and linearity, we get the correspondence between output of a signal with respect to its previous outputs and inputs. The above mentioned equation h of z is called as transfer function of a system. Now let's see more about these. Given the transfer function h of z, we can do a lot of stuff with it. The picture here captures the same. We previously saw how to find the time domain corresponding equation to h of z by applying the inverse Z transform. Now let's see a few more. So given a h of z, one can find the input-output convolution equation, the input-output differential equation, the pole zero pattern. Also one could use this to design a filter based on the frequency response. We can find the frequency response of a given signal by first finding its Z transform and then substituting z by e power j omega. Also one could use this to visualize how a system would look. That is, one could find the block diagram realization. So we saw that given a h of z, we can write it as y of z by x of z, and then on cross multiplying and applying the inverse Z transform, we get the following relationship. This equation here is called as the IO difference equation, which basically shows the relationship between y of n and the system's previous outputs and inputs. Now let's see block realization in parallel form. Consider a h of z Here we take h of z to be equal to 5 plus 2z inverse by 1 minus 0.8 times z inverse. This can be split into a form of a0 plus a1 by 1 minus 0.8 z inverse. And on equating and simplifying, we get a0 to be minus 2.5 and a1 to be 7.5. Now applying z transform to h of z on the split simplified version, we get h of n to be equal to minus 2.5 times delta n plus 7.5 times into 0.8 power n u of n. Here h of n is nothing but the impulse response of the system, which is obtained when an impulse function delta of n is given as input to the system. We also know that u of n is nothing but collection of impulses for n greater than 0 at n's. This diagram here shows the parallel form realization of h of z, which is nothing but this equation. So first, given an input x of n, we multiply it with minus 2.5 and then again scale it with 7.5 and then introduce time delays to it. So first it would be delayed by 1 second, which would be summed up here, and then again by 2 seconds, 3 seconds and so on. And thus all these terms are summed up with minus 2.5 times x of n to give the output y of n. There is one more type of block realization called direct form realization. So what we did previously was we visualized the output of a system using some functions and the current inputs to the system. But now we have extended this concept to represent the given output of a system as a linear combination of its previous inputs and previous outputs. This can be done by representing h of z as y of z by x of z, cross multiplying them and applying the inverse Z transform. We get this equation. This block diagram shows the direct form realization of h of z, where you can compare this diagram to this equation and you see there is the same. So you scale x of n by 5 times, you delay it by 1 second and scale it by 2, add up. The previous output which came just before this is taken, scaled by 0.8 times and is again added back to get the present output. Another important concept is the zeros and poles. So given a h of z, the value of z for which the numerator becomes 0 is called as the 0 of h of z, while the value of z for which the denominator becomes 0 is called as the pole. Here if we see in this given example, where h of z is 5 times 1 plus 0.4 z inverse by 1 minus 0.8 z inverse, the 0 is z is equal to minus 0.4, whereas the pole is z is equal to 0.8. That's because for z is equal to minus 0.4, numerator becomes 0, and for z is equal to 0.8, the denominator is becoming 0. In geometric representation of ROC, zeros are marked by these white circles, whereas poles are marked by these black circles in the z-plane. To help understand this better, consider a 3D plane with its axis being the real part of z, imaginary part of z, and the another axis being the magnitude of x of z. So whenever there is a pole in the z-plane, x of z shoots up to infinite as the denominator of x of z becomes 0, while magnitude of x of z becomes 0 at the zeros of x of z. Here, when we do such a realization for this example, we find that at z is equal to 0.8, the value on the z-axis would become infinite, whereas at z is equal to minus 0.4, it would be 0. The circle z is equal to e power j omega represents the Fourier spectrum of a given signal. We have seen this previously. So the values which lie on the circle z is equal to e power j omega correspond to the Fourier spectrum series of a given signal x of n. We can actually try to guess the spectrum of a signal by looking at its zeros and poles. So consider a signal h which is time limited. We find the Z transform of h, that is h of z, by using the formula sigma h of n z power n from n is equal to minus infinite to infinite. But here we have points only for n corresponding to 0, 1, 2, 3, and thus h of z would be this. H of z here can be factored into these three terms here. We know that Z transform becomes equivalent to dt of t when z is equal to e power j omega, and substituting the same here gives us the corresponding Fourier spectrum. H of omega would become this. So for h of z, if we try to find the zeros, we see that the zeros are minus 1, minus 2 and minus 3. Only minus 1 lies on this circle, on this unit circle. For z is equal to e power j omega, this unit circle here is represented by z is equal to e power j omega. And when we try to plot the magnitude of h of omega with omega, we see that at omega is 0, the value is 24. You can just check it by substituting here. And for omega is equal to pi, that is corresponding z is equal to minus 1, we find an exact 0 for magnitude of h of omega. Thus, at the points of zeros of h of z, Fourier spectrum would be 0 at the corresponding points. This diagram here shows the block realization of h of z corresponding h of omega. We know that z is equal to e power j omega represents a unit circle, as one can see by saying mod z is equal to mod of e power j omega, and mod of e power j omega is 1. So mod z is equal to 1 represents a circle with radius 1 centered at 0. The range of w would be from 0 to pi and 0 to minus pi, or one can say it is from 0 to 2 pi. Consider a signal x of n, which is e power j omega naught n into u of n. This is of the form a power n u of n, and we know its corresponding Z transform to be 1 by 1 minus a Z inverse, and here a being e power j omega naught, we get the Z transform of x of n to be this. Now if we try to evaluate its spectrum by substituting Z is equal to e power j omega, we get x of omega to be this, and then on taking terms common, we get this. So here we see that z is equal to e power j omega naught is a pole, as on substituting the value, the denominator of x of z is becoming 0, and corresponding to that, omega is equal to omega naught represents the same pole. Thus at omega naught, mod of x of omega tends to infinity, that is, it leads to a discontinuity in the graph at this point. So wherever the poles are there, we get a discontinuity in the graph, or the graph shoots to infinity at that point. Thus we could try to make an estimate of the spectrum by looking at the zeros and poles in the Z transformation. Okay guys, thank you for watching the video. We will discuss furthermore on these topics in the coming videos.